In today's video, we want to talk about sum estimation theorems. So in the last video, we covered the integral test, and the integral test was the second of many different tests that we can use to determine if a series converges or diverges. In particular, the integral test looked for functions that were positive, continuous, and decreasing. So you can think of the family of rational functions, the p-series, as a great example of something to use the integral test for. So in this video, we want to look at the integral test a little bit more in the context of sum estimation. Now for geometric series, as I said earlier, we can determine exactly what a series converges to if we have a converging geometric series. However, with other series, it's a little bit harder to do that. So for some of the series that we use the integral test for, as you probably have seen, we need to use more rudimentary approximation tactics instead of finding an exact solution, because of course we cannot do that. Now, I'll be honest, I'm not a big fan of these approximations. I am a lot more comfortable and just familiar and happy with dealing with real numbers and all of that, but we're going to pull out our calculators for this one time, and we are going to do some approximations. All right, let's get started. So I just threw it all up on the page. So again, we take the same ideas as the integral test, so it needs to be positive and decreasing, it needs to be continuous, but it also needs to be convergent. So using this estimation theorem, it revolves around the fact that you already know it's convergent. So maybe you already used the integral test earlier to make sure that it's convergent. I don't really care. And we also have the correspondence of a sub n to f of n. And then additionally, we define this quantity r sub n, so that's the actual value of the sum minus a partial sum, minus an nth partial sum. So if we have this r sub n, which is the total sum minus this nth partial sum, then the integral between n plus 1 and infinity of f of x dx is less than or equal to r sub n, is less than or equal to the integral between n and infinity of f of x dx. Okay, so if we have a series, if I have a series right here from n equals 1 to infinity of a sub n, then we are immediately going to be able to use that integral between 1 and infinity of f of x dx, because our a sub n is going to be mapped to f of x. We can plug that directly into this little thing here, except instead of 1 like we have there, we're going to go to n. And that can be easily modified depending on what sort of n we want to deal with. And an important thing is, for this next one, in the second formula, we're going to be needing to calculate partial sums. So that can be done manually. It's usually not going to be anything more than 10 or 15, so that shouldn't be super tedious. I would think you could use a calculator for that, obviously. So the second theorem says that if I have an nth partial sum, and I add that with the integral between n plus 1 and infinity of f of x dx, then that is less than or equal to the sum, which is less than or equal to the partial nth sum plus the integral between n and infinity of f of x dx. So that's a great way to approximate this guy right here. Okay, so then here, of course, we have our error estimates. Okay, so let's get started. So here we have Stewart's calculus book, very popular in colleges for Calc 2, chapter 11.3.6. So this is the integral test section, example number 6. And we're kind of going out of order with this book. At this point, we're doing series before we do parametric equations. That's next. But they do it after. Something interesting, I guess. Anyways, so we are going to use n equals 10 to estimate the sum of the series between 1 and infinity of 1 over n cubed. All right, so we can look at this, and we can determine that this is some sort of rational function. It's a general rational function with no transformations And just like 1 over x, it's just a higher order version of that, or a lower order version of that, I guess. And it asymptotes towards y equals 0 as x goes to infinity. You can kind of imagine what it looks like, just since it's in that general family of curves. And it's pretty obvious that that converges, since that is a p-series, and our p power is greater than 1. Of course, when it's equal to 1, then we have the harmonic series, which of course diverges. Right, so what do we want to do here? So we want to plug this into that second theorem that we had there. So we have that the 10th partial sum plus the integral between n plus 1, so the integral between 11 and infinity, 1 over x cubed dx, is less than or equal to the sum, is less than or equal to the 10th partial sum, plus, we only need one plus sign there, the integral between 10 and infinity of 1 over x cubed dx. All right, so let's tackle this integral, and we're going to tackle this integral, it's going to be very easy, but we're going to do it between n and infinity, because as you can see, we have both 10 and 11 down there, so it's just going to be easier if we get an expression for n, then we can plug it in both places. So what we get is we get that the integral between n and infinity of 1 over x cubed dx is equal to negative 1/2 over x squared, or 1 over 2x squared, I guess. We evaluate that between infinity and n, or n and infinity. If we plug in infinity, well, this is going to get super big. We're dividing 1 by a super big number, so that goes to 0. So we'll get 0 minus negative 1 over 2n squared, plugging in n there, and that is going to give us positive, because these negative signs cancel out, 1 over 2n squared. Okay, so now we have a nice expression, and we can plug this into our formula, and then we're going to plug in 11 and 10, so we're plugging 11 and 10 into the left and right hand sides. So we get the 10th partial sum plus 1 over 2 times 11 squared is less than or equal to the sum is less than or equal to the 10th partial sum plus 1 over 2 times 10 squared. Okay, so now what we want to do is we want to find what our 10th partial sum is. I don't particularly care how you do this. I don't want to do it here just because we need to plug in a lot of numbers into this little formula there. And that's something that you can easily do on your calculator, so I'm not going to waste time doing that now. But anyways, from this, if we plug this into our little formula, our little inequality, we determine that the sum is somewhere between 1.201664 and 1.202532. Now, of course, this is a fairly good approximation, I think. And we can now kind of take the midpoint of this. We can estimate kind of error bounds as well. And we get that the sum is going to be at about this midpoint, which is 1.2021. All right, so that's all I've got for this video on the estimation theorem. In the next video, we are going to be covering the comparison test. So that's a different type of test we can be using